This equation is the generalized capacitance. C is equal to A into epsilon naught into epsilon naught divided by D. So generally, whatever capacitance is there, we will design with the help of the cross-sectional area and then the distance between the two parallel plates. Okay, based on that only the design procedure will be there. Okay, so that is this equation signifies us. And then these are the geometries in that the first one. Okay, for first one we have fully derived and we got that expression. At last I will put you that expression so that it will be definitely useful for you. Today's class we going to move for all five geometries and what is the resultant expression comes for each geometry. Okay, not full derivation is required. Okay, just I will explain about the geometry and I will explain you about all the equations. Okay, let me go with the second case. What is the second case? The capacitance. Students, if anyone joining or anyone waiting outside, please let me know. You can interrupt me. Okay, so don't wait until that, and you can tell me in before. And also, if you're having any doubts or any clarification, you can let me know. Okay. It should be a lively and interactive session. It is not that is what only one person has to talk here. Okay, you can contact at any time. Okay, the capacitance of a parallel plate capacitor. Okay, parallel plate capacitor having a three dielectric media, having three dielectric media. That means what? There is normally the capacitance will be like this. Okay, capacitance will be like this. But here, three regions in between. Okay, suppose I am considering this is first region, second region, third region. So this has the epsilon R1, this is epsilon R2, this is epsilon R3. So don't get confused with this epsilon. There is a three category of epsilon you have studied. The epsilon is for the signifies or noted for the electric field. Here there is a three category of epsilon you will represent. Epsilon is nothing but permittivity of the medium. Epsilon naught is nothing but the permittivity of the free space. Epsilon naught means.
So I had a question.
Yeah, please tell Livingston.
Yeah, so does it matter if you place the electric medium perpendicular to the plates, or will you teach about it later in class?
Actually, in your syllabus, only the capacitance effect alone we're going to study.
Yes, sir.
Okay, capacitance effect alone you study, not concentrate on the field. Okay, so
Oh,
why?
okay. Yeah.
Okay, so why that epsilon and mu is coming? I'm telling. Okay, so epsilon is for the electric field, mu is for your magnetic field. Okay, since it is it relate to the dielectric medium. Okay, so you should not get confused why this epsilon parameter is coming inside. Okay, I understood your question. Okay, so that you will get in the advanced level of papers.
Yeah, sir. Yeah, actually, my question was related to electric field. Yes, okay, sir. I get it.
Yeah.
I get it, sir.
So for that question also I will answer later. Okay. But right now I will tell what is the basic fundamentalities is going on. Okay, so three categories is there. Epsilon is for the general medium. Okay, general medium. Okay, and this epsilon naught is for the free space, and epsilon naught is for the relative permeability. Sorry, permittivity. Okay, relative permittivity. So mostly for the dielectric materials it will come. So the dielectric material mostly not only in the capacitor, okay, some of the electronic gadgets it will be there. So it will be act as the protective substrate material inside this conducting element. It not get damaged at any of the potential. Okay, that is the main functionality of this dielectric material in these type of devices. Okay, you can see here there is a three dielectric material. Maybe if we mainly concentrate on what are the materials, there are different categories of materials. Maybe I don't know in upcoming what semesters we will study about the electromagnetic laboratory. Okay, but you not deal with the lab for this subject. But when you come with the laboratory, each are considered as the strip line. Okay, each are considered as the strip line, and for that strip line, the material may be different. That is the chemical composite material may comes different. Okay, but the thing is that we going to achieve what is the value of the total potential. So how we did in the previous case, just I will recap the previous one. You can see the basic equation what we defined for each medium. So there is two medium here, like two dielectric mediums are there. So it will be related with the potential capital V. So here E1 D1, then E2 into D1 D minus D1. In similar here also we are going to make it like D1, D2, D3, and we have the different potential in the respective regions, and we are going to sum it up all. And what is the dielectric flux density? The dielectric flux actually the flux density why we relate here means whenever the potential applied to this electronic devices, okay, the flow of electron will be conduct. Then after it will be induces the flux. Due to the flux only, the electromotive force will be developed. So the flux density is defined as the charge per unit area Q by A. So where D is nothing but epsilon into E. Generally, we will relate like ds but epsilon into capital E. But we have to relate with the respective medium. Okay, so we are mostly our concern is the dielectric medium. So what only the epsilon is denoted as epsilon R1. Similarly, the field related to the first region is E1. So we are getting that expression and summing up two thing and sorry two value of the potential V1 and the V2 respectively, and then we have rearranged this expression and substituted in the capacitance. Okay. In similar, this procedure also will be followed. Okay, but I'm not going to do the full step. So just to remember the formula for this A epsilon naught. So please see in before also A epsilon naught is the epsilon naught is the epsilon R1. Okay, epsilon R1. So if epsilon R1 is air, please see if epsilon R1 is the air, then numerator epsilon R comes or not? Definitely not comes. It is equal to 1. Okay, it is equal to 1. So then the value for this is C is equal to A epsilon naught divided by epsilon R1. Okay. So this is the formula we have attained in the previous case. So similarly here, numerator will be the same, but denominator has the three different dielectric materials. So it can be related as D1 divided by epsilon R1 plus D2 divided by epsilon R2 plus d3 divided by epsilon r. So this is your capacitance effect of your capacitor having a three dielectric material. Let me go with the third case. Okay, third case. Actually, Livingston asked one question. For that also I will answer. Okay. Suppose the field, he asked about the electric field and the magnetic field, how it will be inside this dielectric material. Okay, that is I will explain you. Suppose the capacitance is like this. Okay. Suppose this is your capacitance. Okay. So consider whatever dielectric media, it may be a 2 or 3, whatever it may be. I'm simply putting as like this. Okay. So the capacitor is used to store the charge. Okay. Suppose I'm considering this is your positively polarized plate, this is negatively polarized plate. So it will come electron from the negative polarity. Okay, it will come like this only. Once the electron comes, okay, so please see once negative, the majority carrier for the negative is electron, and for positive it is hole. Okay, so when it combine at room temperature, please see at room temperature only all semiconducting material will conduct. Okay, so whenever this type of dielectric material is there inside this parallel plate, okay, so this will be diffused together. Okay, once this diffused together, the field will be generated. So if I am telling this E plane will be generated in this direction, then the magnetic field will transverse with each other. Okay, so this will be alternatively changed for different interval. Okay, different interval. So as per your capacitance equation, so what is the definition of the capacitance? It is nothing but the C is equal to Q by V. That is charge per unit potential. Okay, so per potential, that is potential at 1 second. Okay, the potential at 1 second. What is the charge accumulated over to this capacitance? So the add next interval, like that it will go up to nth interval. Okay, so it will be like what keeps on increasing the charge level with respect to it will be increasing keeps on. Okay, once the potential drop down, the potential drop down at that time it will be gradually releases the charge. Okay, suppose this is the charge level from the lower intense region to the higher intense region. Okay, so this is your V1 and this is your V2, so or Vn. Okay, some maximum value of the potential. Once the potential level increases, automatically your charge level will goes high. Okay, so whenever I will tell one best example. Okay, so in generator, the best example is the generator or UPS in your home. Okay, so during the potential or the power, what it happen? It will accumulate the charge in your UPS power supply. If one day fully the power shutdown is there, or 1 day or 2 days, so that UPS may be sustained up to just 3 to 4 hours. Okay, so the time that is the power cut at some 8 p.m. night 8 p.m. Okay, up to 12 or 11, the signal strength of this capacitance effect will be good. Okay, at that time it will be at the peak when the electrical things are being regularly utilized. What happened? The charge level will be comes down. Okay, At one instant of time, it will be entirely, the charge accumulation will be fully drained. Okay, that will be happen due to the field is there in your capacitor. Okay. So this you will study in alternative electric and magnetic field with respect to the time. That has been clearly explained by using the Maxwell's theorem. Okay, Maxwell's theorem. So let me go with the next third one is the capacitance of the capacitor. Okay. Let me move with the next geometry called the isolated sphere. So everyone aware about the geometry of the sphere. It has it look like the coconut. Please imagine how the coconut will be in 3D. Okay, in all three dimensional, it have the equal radii. Correct. It have the equal radii. Suppose I will write the what is the thing we're going to see, that is the capacitance of an isolated sphere. Okay, for this isolated sphere, what is the capacitance? Okay, so you will get for this as um, suppose consider this is the one. It has it will be orient in all three direction having the same radii of R. Then what is its capacitance? Okay, it has the common radius, common diameter. Okay, only thing is that it will change the geometry. Unless it will be a same, then what is the capacitance? So you can ask one question: what is this? It is this is the shape of the capacitance, or it is the shape of the electric material. So absolutely, it is the shape of the isolated capacitance. Okay, so this type of capacitance also available in real market. Okay, so it has uh, uniform distribution all over the thing. It will be simply called as the isotropic effect will be conducted in this capacitance effect. So the formula for this is C is equal to 4 pi epsilon naught. Okay, it is your the medium. Okay, if it is general medium is there, then we have to denote as 4 pi epsilon into R. The unit of the capacitance is the Farad. So where epsilon is nothing but what epsilon naught into epsilon naught. Actually, before also one thing I forgot to tell. Actually, here in epsilon naught numerator is there. Here also epsilon naught is there. Okay, so please see here. Okay, so we are substituting for this thing only. Okay, so here epsilon R will come. That is epsilon R2 will come. Okay. If you do simplify this thing, what happened? Epsilon R1, epsilon R2, epsilon R3 comes to the numerator. Okay. So if I am considering the relative permeability of air, value is 1 only. If you substituted over to the above expression, C equal to 4 pi epsilon naught into R. Okay, so this is the formula for this given geometry. Okay, so let me go with the next geometry called the concentric spheres. Okay, concentric spheres. For concentric spheres, the geometry almost look like this only. But please imagine how the tires will be there. How the tires will be there. Let me see the fourth one. The capacitance of concentric sphere. So it will be the same geometry, but in between only hollow gap will be there. Some thickness will be there. Where in above have the minimum or the thin thickness, here you have the thickness like this. Then what is the effect of the uh, capacitance for this concentric sphere? So for this concentric sphere, okay, the formula will be like this: C is equal to 4 pi epsilon AB divided by B minus A. Okay, AB divided by B minus A, where A is nothing but the inner radii and B is nothing but the outer radii. Okay, so this is nothing but the capacitance of the concentric spheres. Okay, concentric spheres. Come to the next geometry called as the coaxial cables or the cylindrical geometry or cylindrical coordinate system. The next one, the capacitance of coaxial cable, that is called as okay. Let me see the geometry how it will be look like for this type of devices. Please imagine how the cylindrical size will come. Everyone know that cylinder will be like this, but it has this some thickness. Okay, so mostly in your home also, and the thickness of the wire maybe comes like this. Okay, so in this, what is your capacitance effect? Okay, so the formula will be like this. Here also, just I will draw the one portion so that I will give the notation of the radius. The inner radius is A, and the mid of this one is nothing but R, and outer radius is nothing but B. Okay, so then what is the capacitance? Just see the formula alone. C is equal to 2 pi epsilon naught into epsilon naught whole divided by ln B by A. Okay, so this is nothing but the capacitance of the coaxial cable. Similarly, the next one is the parallel plate capacitor or called as the transmission line. Okay, and general transmission line also the capacitance effect is one of the predominant one when we going with the alternative current element. Okay, so then the fifth one is that capacitance of a parallel plate transmission lines. Okay, transmission lines. So what is meant by a transmission line? A transmission line is a one which connecting the transmitter and the receiver, whether it may be a whether it may be a wired or wireless medium, whatever it may be. But we mostly prefer the wireless medium. So then, what is the capacitance? So for this, what is the formula I will tell? So the capacitance C is equal to okay. So the formula is C is equal to pi epsilon naught whole divided by ln of T by A. Okay, so C is equal to pi epsilon naught whole divided by ln of d by a. So this is nothing but your formula of parallel plate, or otherwise known as the transmission. Okay, and then you in electronic engineering, you know basically what is the arrangements of a parallel plate capacitor, the capacitor in series, etc., etc. That is a basic fundamental one. So that one we no need. Okay, that concept we are going to skip it. Okay, so that is not in your syllabus also. So the next concept is called as electrostatic energy. Energy. So when before getting to this content, what is the energy level of one teacher in a class? Okay, so definitely what happened at beginning, the intensity level or voice level will be very huge, since you know that the subject knowledge, he will teach what according to the strength level of that teacher, correct? So even then he has the energy to when he continuously telling or giving conversation with the student, at last he will get tired, so he not have the health drinks, so he will uh, okay, so he will boost up the noise up to that. Okay, so let me move ahead with the what is this electrostatic energy. So the electrostatic energy is nothing but the work done. Okay, it's nothing but the work done to build up the charge. To build up the charge. Suppose electrons. I am considering this is the electron, one big electron, somewhat moderate electron, some smaller. When the electron is moving toward this direction, it will bombard with this electron, and it will bombard with this one. This is very very small. Okay, it will be bombarded with each other. Similar, like one example, I will tell one healthy, like everyone saying WW, that person is huge and he is very gigantic. When a person like us without doing exercise or normal person, if I am moving or touching, pull him or push him, okay, so I cannot do it due to his stability. Similarly, here also, when the big electron atom will be touched with the smaller one, it will be easily moved toward this direction. Okay, but
So,
please, yeah, please tell.
but electrostatics generally means if like electron is stationary, right? So, but in this case, it's moving.
Yeah, actually, in electrostatic, as you told, it is a static. Okay, so I'm talking in a time varying case also. Okay, in time varying case, the electron moving and how it will become in real time with respect to the time. Okay, but the equation expressed for the static condition. Okay, for understanding, I'm telling that once you are applying the potential towards the capacitance, okay, at a fixed time, okay, at a fixed time, then a fixed energy will be stored in that capacitance element, as you told. Okay, as you told. But when the electron, sorry, at the variable time, okay, so the electron will be moves. So for theoretical purpose only, we are studying about the electrostatic principle and the magnetostatic principle. Okay, but It is not possible in real. Okay, so everything in a dynamic manner only. So for dynamic case I'm explaining. Okay, but you should know the difference of equation for static and dynamic. Your question is correct, Darshan. You got my point?
So Samuel, so yes, I got.
Yes, yes, yes. Yeah, thank you, Samuel, for your next question. Okay, so okay, so how it can be given means the capacitor stores the electrostatic energy is equal to the work done to build up the charge. Okay, to build up the charge. That I define once again, and we will move towards the what is the final expression for the electrostatic energy. Okay, maybe this explanation will be useful when we go for the dynamic case. So, okay, so that the capacitance, okay, capacitor stores the electrostatic energy is equal to the work done to build up the charge. So it can be literally given like this. So that is potential V is equal to dW divided by dQ. Okay. So it is the normally we will give. Okay, this is the as per the definition equation, we are giving work done per unit charge to build up the charge. So this is equal to the potential. But how you will relate the capacitance? How we will give the capacitance? The capacitance is equal to Q by V. Okay, the capacitance is equal to Q by V. Okay, so then how you will rearrange this equation? Okay, how you will not rearrange, how you will solve this equation? Okay, let me define what is meant by the work done. So dW is the partial work done, that is the differential work done. The differential work done is given like V into dQ by equation 1, right? Equation 1. By using the capacitance definition equation, this can be solved like dW is equal to Q by C into dQ. When we solving this equation, we will get the what is the electrostatic energy W. So the W is nothing but your electrostatic energy. Okay. So when we solve this equation, we will attain one expression. So that we will complete in the next class. It will take some 5 to 6 minutes. Okay. So now it's the time for completing our session. Okay. So next class we will complete this electrostatic. Then we will go with the energy density concept. Followed by that, we will move ahead with some Poissons and the Laplace equation. So, if you're having any doubts or any queries, you can ask at the end of the session after taking the attendance.